Alright, this is the first formal video lab report for LB274 entitled Levitating Balloons. The main question of this lab was to calculate how the charge, Q in coulombs, on a pair of charged balloons that levitate and exert electric forces on each other. To answer this question, we needed to figure out a way to calculate the magnitude of charge on each one. Our hypothesis was that given the distance and electric force, rearranging Coulomb's law gives us an equation to calculate the charge on one balloon in our experiment. That equation is Q equals the square root of the distance squared over Coulomb's constant times the electric force. Our experimental design was to essentially build a cage for the charged balloons, one fixed and one free. We used 3 ring stands, 3 meter sticks, string, 2 balloons, and a tape measure. We built the cage with a string support to prevent discharge. We then rubbed each balloon against the sweater for 60 seconds simultaneously to give each balloon equal charge. After the balloons were charged, we placed the fixed balloon on the string support and placed the free balloon on top. They repelled each other as the electric force upwards balanced gravitational force downwards.
We had a number of assumptions concerning this experiment and the interaction between the balloons and surrounding objects. Firstly, we assumed that the charges on the balloons were exactly equal. Second, we assumed that there was no electrical discharge from the balloons after they were charged. We also assumed that the balloons would behave as point charges. And lastly, we assumed no external forces would act on the balloons.
Our physical models consisted of a free body diagram and a system schema. The free body force diagram had an electrical force acting upwards that was exactly canceled out by a gravitational force pointing downwards. Our system schema consisted of the 2 balloons, which have electrical charge acting against each other, and Earth, which is exerting a gravitational charge on both of the balloons. We rearranged Coulomb's law to solve for Q. Because we charged the 2 balloons in the exact same manner, they were equally charged and should be equal. Then, using the F-net and Newton's second law, we were able to solve Q as shown.
We hypothesized that when the balloon reached an equilibrium point with the other balloon, the downward acceleration of the free balloon was 0, and the net force would be equal to 0, allowing us to set the electrical force equal to the gravitational force. However, the balloons may have reached an equilibrium point with no acceleration due to the electric interaction between the sides of the cage rather than just the repulsion between the 2 balloons, which may have resulted in our data being skewed. We hypothesized that this could be remedied by using an uncharged insulator as the cage walls, as the charge wouldn't discharge on the insulator as it possibly did on the string. By manipulating Coulomb's law, we were able to determine the charge on each of the balloons theoretically.
Our conclusions were that, although the experiment may have had skewed our data due to the electrical interaction between the balloon on top and the string cage, this setup was only theoretically possible. This observation was gathered after we completed the lab and therefore could not be remedied by taking tracker data. If this lab was repeated in the future and our same system would be used, the cage would need to be replicated out of a material that does not interact electrically.